recording.
Okay, so it's okay. Good morning, everybody. I'm just to introduce myself. I'm Taleb Bou Hamdan. I'm doing a PhD in Mishnah in collaboration with Laboratoire d'Informatique et Automatique pour le Système, Mercère de Poitiers, under the supervision of Dr. Guillaume, Mercère, and Coirault, and I'm working in Mishnah with Thibault, Dairay, and Pascal Trombier. And today I'm going to present about our work in tracking distributed parameter system dynamics with recursive dynamic mode decomposition with control. So let's starting with explaining about my PhD project. Just as a note before starting, I started my PhD officially since 4 months, since the beginning of the year. But I worked with Mishnah on the internship for my master thesis for 6 months, and after that I worked with Lias for 4 months on the same subject. So for now it's been a year. So the subject of my PhD is controlling a calendaring process. What is calendaring process? So in the wheel industry in Mishnah, in the first step, we have to press or calendar the material so that we obtain from the bulk material, we have thin material, and the material is pressed in between wheels. So just for simplicity, this is the process. And for simplicity, we have the calendaring wheels. So the calendaring wheels are rotating. We can manipulate the speed, the rotational speed of the calendaring wheels. And the material is being pressed in between so that we have thin layers of the material. This material is rubber. And the rubber itself is characterized by being viscoelastic. And what we are trying to control is the temperature of the rubber, so that the temperature doesn't go above like a maximum. We have a maximum limit and a minimum limit. Below this minimum limit, the rubber will solidify. Above this temperature limit, the rubber will rupture and it's of no more use. So as I've said, we can control the calendaring wheels. And in fact, because it's a fluid dynamics and fluid control, we consider that, okay, we have normally in fluid dynamics, we consider it's a big assumption, but we've taken that we know the temperature and all the fluids inside this domain, because we have simulators for this one. So for now, we consider that we know all the states, all the temperature inside the domain. So this, as I've said, it's because it's rubber, we have viscoelasticity, then the system is characterized or suffers from nonlinear thermomechanical coupling. How is the coupling? The temperature inside the domain, inside the rubber, is a function of the velocity of the calendaring wheels and the viscosity of the rubber itself. And the viscosity is a function of the velocity, specifically the gradient of the velocity of the calendaring wheels and the temperature of the rubber itself. So what we are trying to do, since our aim is to control this process and to control the temperature, we start by the system identification, and our aim is to find a low-dimensional representative model. So, since we are explaining today about the system identification, our system dynamics are governed by nonlinear partial differential equations. I said that we have a simulator, and for this simulator, the simulator simulates the partial differential equations. I know all the states inside my domain, but instead of going to discretizing the partial differential equations where I can't reach anywhere nearly, so our solution track is to apply data-driven modeling along with model order reduction. So we will use the data from the simulator, we will do the data-driven modeling, and accordingly, we have all these states. These states are like, we have a huge state vector, so we'll apply afterwards the model order reduction. And so my system boils up to, I have my system, the input Q is the calendaring speed, the speed of the calendaring wheels, and the states X are the temperature at each node inside this domain. And at the end, my discrete time system model will be as a function of X at the instant K plus 1 is equal to AXK plus BQK. So now I want to find the matrices A and B. So an outline for today, I will start with classically in literature, which is trending now and which mostly used in fluid dynamics, is the method of dynamic mode decomposition. So I will start with an introduction of the reduced dynamic mode decomposition with control, which is composed of 2 parts. The first part is dynamic mode decomposition with control, And the second part is proper orthogonal decomposition for model reduction. But these methods are applied on a batch snapshot matrix and a batch data set. So I will try, we have introduced a method which allows us to update what we have recursively. So we will do a recursive proper orthogonal decomposition and then introduce the recursive reduced dynamic mode decomposition inflow. And test them on some examples and finish up with a conclusion and some prospects on how we are proceeding. Okay, so I will start step by step with the reduced dynamic mode decomposition inflow. So first I will introduce the dynamic mode decomposition. As I've said, we have a nonlinear model. So in the nonlinear model, let's say we have the state vector x tilde, dx tilde by dt as a nonlinear function of x tilde. But Kauffman theory states that any nonlinear system can be formulated via an infinite dimensional linear model. So I can write dx by dt as a linear function of x. And with Euler discretization, we have xk plus 1 is equal to a xk. So if I have xk plus 1 and xk, I can estimate a. So the dynamic mode decomposition says that, okay, let's consider that we have a snapshot matrix of these states over anti-instance. We do our simulations for anti-instance and we collect the data in the axis snap containing the snapshot, the values of the snapshot on time instant 1, 2 until anti. We split the axis snap into two matrices, x1 and x2, such that x1 contains the first anti-1 instance snapshots, and x2 contains the last anti-1 instance. And by that, we can see that each one of these vectors is one step ahead of the corresponding vector in x1. So x2 is a one step ahead version of x1. I have x2, I can write that x2 is equal to ax1. I have x2, I have x1, I can estimate a, and thus a can be estimated using the pseudo inverse of x1, which is denoted as x1 plus. So a is equal to x2, x1 plus. And x1 plus, the pseudo inverse, can be found using singular value decomposition of x1. I will use multiple times the singular value decomposition, so that's the first one. Okay, but since we're dealing with a control process, so the input is not 0, so I have q. And for this, we have the updated version of the DMD, dynamic mode decomposition. They introduced for it the control, so it's DMDC. So the system model is not anymore xk plus 1 is equal to axk. It is xk plus 1 is equal to axk plus bqk. The same as before, if I know xk plus 1 and xk and qk, I can estimate a and b. So splitting the snapshot matrix that I have, x snap into x1 and x2, collecting all the inputs that I've used to generate the axis snap and stacking them in an input matrix Q, I can write that x2 is equal to ax1 plus bq, some reformulation, vertical concatenation of a and b, and horizontal concatenation of x1 and q. x2 is equal to ab multiplied by x1 cube. As before, we have this matrix x2, we have the matrix x1 cube. So we can estimate ab using the pseudo inverse of x1q, and ab is equal to x2 multiplied by the pseudo inverse of x1 and q. And we can split a and b. So we've estimated a and b using the DMDC method. Okay. So after introducing the DMDC, we want to test it and validate it on a calendering toy example. So for the calendering toy example, we use the heat diffusion PDE, which is an easy way to see the variation of temperature, where the temporal variation of temperature is a function of the spatial variation of the temperature plus a source term. So the state vector x that we've been speaking about at each instant represent the temperature values along the length Ly, which was discretized into nx values, and nx in our case is taken as 100. Using discretization for the temporal variation and the spatial variation, we get a linear high fidelity system model of order nx, which is 100 here, and we've chosen some values of q source so that we can simulate the system and collect the axis snap. Now we have the axis snap, we have the q source, we split axis snap into x1 and x2 as said in the previous slide, and we can find the a and b, estimate a and b. Okay. We've estimated our system. Now we have the A, estimated A, and we have the high fidelity matrix A that is from the discretization. One way to compare them is comparing the eigenvalues. So comparing the eigenvalues, we've plotted here the comparison of the first eigenvalues. And in blue circles, we have the eigenvalues of the approximated matrix A. And in red stars, we have the eigenvalues of the high fidelity matrix A. As we can see, they are almost the same, and by that, the estimated model is accurate and can be used instead of the high fidelity one. Okay, but then now, our model has an x equal 100, so A is of order 100 by 100. Okay, it's 100 by 100. So if it is of an x which is 100, for a toy example, in real life it may go up to 1000 or 10 power 3 or 10 power 4, which is somehow difficult to be used for control. So what we are going to do is move to the next step, which is the model order reduction. And for model order reduction, we have used proper orthogonal decomposition PDE. Okay. So for the model reduction, as I've said before, the identified model order in the toy example is 10 power 2, but in real life it goes to 10 power 3 or 10 power 4 in fluid dynamics. Saying that I know all the states of my system. So our aim is to find a matrix R with a rank R less than the minimum of n x by n t of the initial snapshot matrix, which minimizes the Frobenius norm of the error x snap minus R. So I need to minimize the Frobenius norm of this error. Using a Cartesian theorem, R is equal to x hat in order to minimize our cost function, where x hat is the truncated x snap of order R. So now x hat minimizes the Frobenius norm of the error, and x hat is the truncated matrix of x snap of order R. How to find R and how to find the truncated matrix? We used again the SVD of the x snap. So x snap is equal to U sigma V transpose. Based on the singular values of x snap, we keep the first R singular values, which save most of the energy, and we split U into UR, UE, and the same for sigma and V. So x snap is equal, x hat is equal to UR sigma R VR transpose of rank R this time. And UR will be used for the model reduction step. So we've introduced the DMDC, we've introduced the POD, so let's combine them together to find the reduced DMDC. We have our process model of high order from DMDC. We've said that xk plus 1 is equal to AXK plus BQK. We've estimated A and B using DMDC. We've collected, in order to find A and B using DMDC, we have the axis snap. We again use the singular value decomposition of the matrix axis snap, U sigma V transpose. We keep the first R singular values of axis snap, and accordingly, corresponding to these first R singular values, the first R vectors of the matrix U are the POD modes, which are saved in the matrix UR, which is the truncated matrix of U. As said before, I'm going to use the UR for the reduction step. So the reduced order vector of xk, as denoted as xr for reduced of k, is equal now to UR transpose of xk. Okay, so now I've reduced the vector xk to xr, and substituting in the model of the system model in xk plus 1. So the system model becomes UR xrk plus 1 is equal to AUR xrk plus BQK. But in fact, we use the property of UR transpose, which is UR transpose is orthogonal. So UR transpose multiplied by UR is equal to identity. And this equation becomes xrk plus 1 is equal to AR xrk plus BRQ of k. And AR is the reduced order of the matrix A, UR transpose AUR, and now it's of order R by R. And BR is equal to UR transpose B of order R by NQ. So we've reduced the order from NX to R, combining both the DMDC and the POD. Testing it another time on the same example. So as I said before that I've got the NX I've used for discretization, NX equal to 100. I reduced it to R equal 5 this time. And we plotted the output of the system of both the real temperature is plotted in the red line at each instant, And the estimated temperature is plotted using the blue stars. And as we can see, they are almost the same, and our reduced order system is resulting in very accurate reconstructions. But all this till now is based on a linear model. So what if as I've started my presentation, I've spoken about the nonlinear models. So what if I tested on a nonlinear model and not a linear model, and check the accuracy of all this? So for a nonlinear example, we've taken an example which is based on the Berger's equation, which is a nonlinear hyperbolic equation. It's plotted on the x and the time, space and time. And the space goes from -1 to 1. And we can see, for example, at the 0 in the middle, how the nonlinearities appear, and with the time. So if I use the whole, I consider, okay, I have all these snapshots on all the time domain, and I use them to create the DMDC, and after that, the reduced DMDC and the reduced order estimated model. And I use it again. We can see that they are almost the same, but for example, in the middle, we have like errors here, and the borders of the lines here are straight lines, meanwhile here are not straight lines. So the reduced order model that we have approximately estimated is working, but not highly accurate on a nonlinear hyperbolic equation. But as I've said, we have the whole snapshot matrix. So what if I have, for example, until 0.2, will the model that I estimate work or not? It won't work. Otherwise, this whole method will be just posterior, like for posterior objectives, and won't work for like predictions and online implementation. So if I take like only the first until 0.18, I use this snapshot matrix, which is the initial batch, and I use it to estimate the reduced dynamic mode decomposition with control model. And I use this model on the rest of the time domain. I can see that this one has nothing to do with the approximated reconstruction, has nothing to do with the high fidelity solution. So the whole equation fails here, the whole system and all the methods that I've explained till now has failed in this one. For this, we are going to introduce recursively, how to update recursively the POD and estimating the model using the DMDC, so that our estimated linear model will capture most of the nonlinearities of the model, of the system that you are dealing with. So till now, I've explained about the reduced dynamic mode decomposition with control, based on dynamic mode decomposition with control and proper orthogonal decomposition. It works very accurately on linear models, but it is not that accurate on nonlinear models. So for this, we will introduce the recursive proper orthogonal decomposition, and then afterwards, we will move to recursive reduced dynamic mode decomposition with control. So let's start with, what are we going to do in this step? Everything we've used is a time invariant system based on the complete axis snap, which is a purely offline method. So it won't work online as we've seen before. And so we are going to introduce the recursive update of the system model and the POD modes matrix, so that we take into consideration the changes in the system, which are the nonlinearities, for example, along with online processing. And it may be a like time varying system, LTI system, an LTV system, and not an LTI system. So instead of saying xk plus 1, xrk is equal to ur transpose xk, we will find urk, and we will find at each instant urk and brk. So let's start with the recursive POD. So our aim is to update the POD recursively online. As explained before, the POD starts from the basis of the SVD. We found the x hat, the reduced x using the singular value decomposition and the first R singular values. So at each instant, after we collect a snapshot, we can do an SVD of the new snapshot matrix after receiving a new snapshot. But every instant doing an SVD of nx by nt, which is increasing, suffers from high computational requirements, which is slow processing of order nx squared by nt. So what we introduce is a recursive least squares approach. Specifically, it is based on the projection approximation subspace tracking, which is the PASS method. How to proceed with that? Okay, so our aim is to minimize x snap minus r. We said it's reduced by setting that r is equal to x hat, where x hat is equal to ur sigma r vr transpose. With some formulation, we can say that sigma r vr transpose can be changed and written as ur transpose x snap. So x hat is equal to ur transpose x snap. And in fact, our cost function can be simplified, and the Frobenius norm of the square error between x snap minus x hat can be written as the summation. Okay, let's consider that I'm at the instant I now. I have all the instants before, the snapshots of the instants before. So my cost function becomes the summation of k equal 1 until the current instant I, lambda I minus k, and the squared error between xk minus uri transpose xk. And xk goes from 1 to I squared. And lambda is a forgetting factor, so that it is set between 0 and 1. Normally, it's between 0.9 and 0.9. The closer to 1, the better. And so that we concentrate on only the last part of the snapshots, the most important part. Now, here comes the PASS algorithm. The usage of the PASS algorithm, we use the PASS algorithm approximation. So instead of writing uri transpose xk, it can be approximated by uri minus 1 transpose xk. So our cost function becomes xk minus uri minus 1 transpose xk. I know xk. I know uri minus 1 transpose. Yeah. I know xk. I know uri minus 1 from the step that I've been in, and I know everything here, so I can just find uri using the recursive least squared algorithm. So at each time step, I'm updating my uri. We've updated uri. Now we can proceed to the recursive reduced dynamic mode decomposition with control. We will merge them together to find and then test them. So our aim now, we will do a recursive reduced DMDC. Our aim is to update recursively the reduced identified system xrk plus 1 is equal to urk plus 1 transpose. We've got urk plus 1, xk plus 1 is equal to ark xrk plus brk qk. First, we say, okay, we had in the nonlinear, in the Berger's equation, we had the first 0.18, the snapshots from 0 to 0.18. We use them, we initialize the DMDC, and by that we initialize AR and BR. Then, but as the formulation before, xrk plus 1 is equal to ark, brk, xrk, qk. This can be written as a cost function to minimize the squared error between xrk plus 1 minus ark, brk, xrk, qk. We know this one. We know this. We can find again the ARK and BRK recursively using the recursive least squared algorithm. Testing them on the same Berger's equation. We started with the high fidelity solution. If we tested the offline initial batch, which was until 0.18, it gives us a completely different one. The same for the offline complete batch DMDC reconstruction. It's almost the same, but we have some errors. Meanwhile, if we tested when testing it with a recursive DMDC reconstruction, the recursive DMDC reconstruction is almost the same as the high fidelity solution. We can't even see the error between them. So for that, if we try to qualify the errors, we can see in this one the residual error of the offline initial batch DMDC. It's only errors. There's nothing true in it, except before the 0.18. For the offline DMDC error, it has errors, especially at the lines in between for the nonlinearity and in the middle. In fact, the errors here they are not limited between minus 0.03 and 0.03. They go up to 1.2 and minus 1.2. But because the errors of the recursive DMDC reconstruction are almost in terms of 0.01 and minus 0.02 and 0.02, we have taken this scale for both of them just in order to visualize the difference between them. So qualitatively, we can see the difference and how much the recursive DMDC error is better. So what if, quantitatively, the error? In order to check the error quantitatively, we've used the best fit, which is the percentage of X, which is the high fidelity solution, minus the estimated solution, yes, the square root of this error, divided by the square root of x minus the average of x. For the offline initial batch DMDC, as we've seen, it's completely error. The best fit is 62%. For the offline complete batch DMDC, it's 96.8%. Meanwhile, for the recursive DMDC, it's 99.4%. So it's almost perfect. Meanwhile, the offline complete batch suffers from some errors. So till now, both of them, it worked very good. But on the calendaring to example, what if we test it on our case and on our process? So for this, we're going to revisit the calendaring process. And what we're doing is we're simulating it on a finite element solver, which is Math++. It's a in-house built simulator for Michelin. So we have the two wheels, they are rotating at the calendaring speed, and the domain in between is simulated, and we know we are finding the temperature using the finite elements method. And in my results, I will show the temperature along this straight line. So in this industrial application, what we've done is that I started collecting the axis snap from the in-house finite element solver using step input between 0.5 and 0.9. So each 40 seconds, I'm making a step. I started with the model reduction based on updating the POD using SVD with the sliding window, and then with the post algorithm and compare them. Then I've done the system identification based on DMDC with reduction or recursive DMDC method with reduction, taking both cases to check which one works better. And then just for taking into consideration that, as we've said before, the fluid dynamics, we have like a huge number of states. In this case, the number of states was 8,385. So we have the temperatures at 8,385 nodes inside the domain. And what I've done is that I've reduced it to R equal 5. Directly, I went down directly to R equal 5. And this one, for example, now is applicable if you want to implement an MPC or any type of control. So starting with the POD, starting with the model reduction. So in the red line, in the red dots, this one. With the red blocks, we can see the high fidelity temperature from the simulator. Using the SVD with the sliding window, I plotted it using the blue line, and using the red line, I plotted the temperature that is reconstructed using the past algorithm for updating the POD. In both cases, they are almost the same. So the best fit for the SVD with the sliding window and the past algorithm have yielded 99.7, 99.8, which is almost the same. But the gain in this level is on the execution time. So if I'm using this SVD, the execution time for constructing the UR is 520 seconds. So I just can, for each step, I can go take a coffee. Meanwhile, for the past, it's 0.17 seconds. So I barely
you can't even blink.
Yeah, I can't even pass answers. Meanwhile, for the system estimation, using the recursive DMDC or the offline complete batch DMDC. So okay, I have the complete batch DMDC, which is only for posterior. I plotted the high temperature as before using the red blocks. For the DMD offline complete batch DMD, I've used the blue dotted lines, and for the recursive DMDC, I've used the red lines. As we can see that the recursive DMDC is almost the same as the high fidelity temperature. Meanwhile, the DMD is close, but not that close. It's like we have a difference of 4 degrees in between. So quantitatively, the error of the BFT of the offline complete batch DMDC is 75%. Some may say, okay, but compared to the recursive DMDC best fit, it's not okay. It's for the recursive DMDC, it's 99.4. So we're getting the same results, but using 5 states instead of 8,385 states. And this one is at time 100. So if we go back for the time 100, it's in the middle of the step. So we have all this one in order to reach like somehow the steady state. So what if I do it, for example, testing it directly after the step at like 121 or 122? Okay, for 121, the recursive DMDC kept its accuracy, and it's almost the same. We can see here that it's slightly moved away. Meanwhile, for the DMD, we still have like the 4 or 5 degrees of difference. So the offline complete batch DMDC has suffered more, and the BFT is now 64%. Meanwhile, for the recursive DMDC, it's still good enough. It's 84.6, especially directly after this step. And this goes back for the forgetting things that we're concentrating on the most recent ones. And by that, the introduced method has worked very accurate on our case for the PhD subject. So now we can proceed for the conclusion and prospects after we validated the method. So I've started with the data-driven system identification using dynamic mode decomposition with control. We've reduced the system model order using proper orthogonal decomposition. Then, because we're working on a nonlinear system and its complexity, we have introduced a recursive proper orthogonal decomposition as well as dynamic mode decomposition. We've validated the recursive methods as well as the other methods on a linear time varying example, a nonlinear example, and an industrial application simulator. In fact, for the linear time varying example, we have tested, but we didn't show them in this presentation, and so on for the next steps in this on my subject. Then now we say that okay, we have all these states, we know all these states, but this is not the case in real life because we are now using the simulator. But I can't say that okay, we know them in the real process. So we will take into consideration the output measurement study based on the sensors locations. Then we will study the observer requirements and structure based on the sensors. We will find the observers and implement the observers. And at the end, we will implement the control and specifically the model predictive control implementation. So that's our aim on the long term, on the end of the PhD. And thank you.
Thank you, Taleb. Any questions? Okay.
I have a question, please.
Yeah, go ahead.
How come that it is like the offline method is less performant than the recursive one?
Yeah.
I mean, like I guess it's because there is the ponderation in the recursive one and not in the offline.
Because mainly because on the offline method, for example, in the steps, for example, here, and the offline method, we're taking everything together, all the processes together. Meanwhile, in the recursive one, we are concentrating on the most recent one and just the ones before. So we're not taking the whole stack. No.
And it's easier to implement in real-time scenario.
Sorry?
It's easier to implement in real-time scenario because for the other one, you can even go to a mall and do shopping as we saw in the execution time.
Yes, it depends on how severe the error that we can handle or not. Because for the temperature, I can handle 2 or 3 degrees of error, but I can handle more than 5. The more I go to the upper boundary, the more I suffer more.
Any other questions? If not, well, let's thank Taleb for his nice presentation. So, and thank you also to the audience of the